The purpose of this video is to make sure everybody has a handle on how to compute X and R bar charts. The first part of this video is going to be on using the data that's given to us, the sample data, and then the second part will be using the table that allows us to skip the step of computing the standard deviation by hand for X and R bar charts only. So what you have in front of you is what we went over in class, and I'm not going to go into a lot of detail, but I am going to at least provide the basics here. So what you're looking at is a problem where somebody has taken a bunch of samples of the weight of boxes of cereal, and so you'll notice that the boxes go across the top and the hours go down the left hand side. So notice the hours come down here, that's the number of samples, and then the boxes come across the top, and that is the sample size. And notice I have written here yellow is the sample size. That becomes very important a little bit later. So every hour we go and pull 9 boxes of cereal off the assembly line and we weigh them. And in the first hour you'll notice that we have 17 ounces, 13, 16, 18, etc. And on average they weigh 16.11 ounces. The range is 5, right? We take the high, which is 18, and we subtract the low, which is 13, and that's how we get this 5 here. So this would be considered sample 1. It consists of 9 individual samples. And then we have sample 2, same thing. We take the average, 16.78. Range here is only 1. So we do that for all of our samples, all 12 of them. And then when we get done, we then take all of our means, these are X bars or means, and we sum them down and take the average. So when you sum them down you get 192.41, and then you divide by 12 and you get 16.03. So this value here, 16.03, becomes the X double bar value, or the mean of the means, and 2.22 is the R bar value, or the mean of the range. We are also given the population standard deviation of 1.03. So the standard deviation for this population here, all of these observations, is 1.03. And then we have to convert that into a sample standard deviation, which we do by dividing by the square root of n. So if that's a little bit unfamiliar to you, let me just show you how we do that. We got it right down here. Notice right here I calculate the standard deviation of the sample by just taking the sample, the population standard deviation, and dividing by the square root of n. So I've got 1.03, I divide it by the square root of n, and I get this 0.34. So 0.34 denotes the sample standard deviation. See here, the population standard deviation, which is here, is often given. All you need to do is convert that over to a sample. So that's exactly what I have done here. We're going to then use the sample standard deviation to calculate our upper and lower control limits. So you'll notice here we have the calculation to compute the upper control limit, which is here, where we take X double bar, which in this case is 16.03 right there, plus 3, which is our Z value, and I'll talk about that in a second, times our standard deviation for our sample. So our upper control limit then is 17.05. Now why 3? 3 is what is often chosen in statistical process control because it denotes plus or minus 3 standard deviations. So let's just go down here where I've got that trusty bell curve annotated. So we are interested in plus or minus 3 standard deviations. So that goes from 3 to 2 to a negative 1. Now here we have the mean, and then all the way back out to 3. So So we are considering 3 standard deviations. That's 99.73% of the events that occur. We're going to say those are in control, and they cover this much of our normal distribution. So our upper control limit then, this number we just calculated here, upper control limit, it represents the mean plus 3 standard deviations. And the lower control limit right here is exactly the same. We compute it the same way, except we use a minus sign. And this represents minus 3 standard deviations from the mean, so 15.01. So this is how we compute the upper and lower control limit when we are given the information to compute the standard deviation of the sample. I want you to note also that it is these values over here that I have circled in pink that actually end up being the values that we care about. We are going to consider these values in pink to determine whether they are in control. That's our test values. So we do not go look within here, not in there. We go here inside of this rectangle, and we determine if our observations are 16.11, 16.78, etc. are all within our upper and lower control limit. And you notice probably pretty easily, quickly there, that these two really are not. So that means that our sample is not in control because of those 2 observations. We do not look inside the sample and say, you know, this one is out of control, or maybe this one is out of control. No, we just look inside the pink over here. Just these 2 are what we would call out of control. So a question that you might want to be familiar with for this would be, is this sample considered in control? The answer, of course, would be no, it's not in control because 2 samples are out of control. Sample taken in hour 11 and sample taken in hour 12. And so on the next, from here, will be a quick quiz question. And so just to formally answer the question, is the sample in control? No, it's not in control because hour 11 and 12 are outside of the control limits. One is above and one is below the upper and lower control limits. And then question 2, what may be the assignable cause of variation? Well, we don't know much about this operation at all. All we know is that, you know, maybe the workers might be tired or the tools are worn out or something by the 11th and 12th hour. Okay, so now I'm going to just work quickly these problems here, 1, 2, and 3, just so that you understand how to do those as well. So here I've brought over the problems, and we'll start with 6.1 there. And you notice I just pulled out the relevant information. I said that x double bar is 14, and the standard deviation must be 1 ounce. So we now, the first step we need to do is convert this to a sample standard deviation. So we have to, in order to go from here over to here, we need to take our standard deviation and divide it by our square root of n. And I added there the n of 36. And so this should give us a sample standard deviation of 0.0167. So now we create our upper control limits by using our x double bar plus 3 times the standard deviation of the sample. So we've got our x double bar at 14 plus 3 times 0.0167, which should give us about 14 plus 0.05, which is 14.05 ounces for our upper control limit. And then our lower control limit is going to be the same, calculated similarly, but it's minus 3 times the standard deviation of x bar, of the sample standard deviation. So we'll have 14 minus 3 times 0.0167. So ostensibly it's going to be 14 minus 0.05, and it should give us 13.95. So I went ahead and calculated then the lower control limits. I used the blue here. So you could see that when we calculate the upper and lower control limits using a smaller z value, it makes them a little bit tighter. Notice that the distance between the blue lines, of course, is less than the distance between the two black lines because the limits are a little bit smaller. So in this problem here, they ask us to set the limits at 2 and at 3, and so that's why I went ahead and did that for us. So you'll notice this is, sort of part B, and then this would be part A. So what is the outcome then of having the smaller z value? Well, then that means that the limits are not as wide. Now for this last problem, 6.3, we're going to work. It's slightly different. We're going to have a different methodology that we can use. It makes it a little easier, I think, to do things. So here we identified that the mean is x double bar is 57.75, and I got that from right here. And we have our average range of 1.78. So instead of giving us a standard deviation, instead they gave us a range. So we can use that a little bit like we use a standard deviation by using a slightly different formula for upper and lower control limits. So we're going to use this upper control limit is going to be equal to, instead of before, remember we had x double bar plus 3 times the standard deviation of the sample. Now we're going to use x double bar plus this factor times the range. So let's go ahead and write that out. So x double bar plus the factor A2, that's something you haven't seen before, times r bar. So what we're going to do here is we'll go ahead and start writing out our formula, putting the numbers in, and then I'll show you where you get those factors from. Here we have the upper control limit is going to be 57.75 plus, now let's go ahead and retrieve that A2 factor. So here I am on the next page of your handout. You'll notice sort of down here in the lower right hand corner we can use this, and the only thing we need to know here is the sample size, but that's going to give us our right here, our A2 factor. So let's go ahead back and take a look at our sample size. So I just went ahead and pulled that out. You see up here it says 35 samples of size 7 were taken from the process. So now we'll go to this next page here, and we're going to go here to 7 and pull that factor 0.419 out. I'll put it here. And we're going to multiply it times our r bar, which is 1.78. And then we're going to do the same thing for the lower control limit. We'll have 57.75 minus 0.419 times 1.78. So we'll go ahead and calculate the upper control limit using this D4 factor times r bar, and then the lower control limit using D3 times r bar. So first we'll go over and pull those factors, also using n of 7, so we've got that 1.924 and 0.076. And then I went ahead and put the numbers in and calculated it out for you, so you can see that the upper and lower control limit for the range, of course they're much different numbers, because now we're talking about the upper and lower control limit of a range, not of the entire sample, are 3.4772 and then 0.135. So we pull the factor from the next page using a sample size of 7. Let's just make a note of that. And we plug the factor in and calculate it. So this way we don't have to convert over the population standard deviation to the sample standard deviation. This alleviates that method, makes it just a little bit easier. One restriction for this method is that it can only be done for plus or minus 3 standard deviations. So when we use the factor table, we can only have limits set at plus or minus 3 standard deviations, because the factor table is at 3 standard deviations. Okay, so now I'm going to have a couple of Kaltura questions where you'll answer a couple questions just like this, but you'll want to bring this to class with you tomorrow, because I'm going to have also some clicker questions on this, since we're going to spend most of the day with Amazon, so that's pretty exciting. Okay, so take care.